Yeah, good evening, Sridhar.
Good evening. Can you hear me?
Yeah, I could. So you can make your slides in the presentation mode. It's okay.
Yeah. Can you still see it?
No, probably I think this is a Google Meet. You may have to unshare and open the file in the presentation mode, and then you have to share the window, right? Screen.
Okay. Okay, when I do that, I have two monitors, so let me do this.
Yeah, okay.
Sorry about this.
Yeah, there's no problem. Yeah, it's okay, no problem.
Okay, I should change this. I have two monitors, that's my problem.
Oh, okay. Oh,
Let's see. I can go to the.
yeah, it's coming good. Well, I think
Okay.
so. Let me welcome you again for the sake of the audience here. I just again introduce with you only two sentences. Dr. Narasi Sridhar was undergraduate from IIT Madras long back, and went on to do PhD at the US. Then he moved to DNV as the vice president of the R&D, or he was heading the R&D section of DNV throughout the globe, and had very wide experience. In addition to that, he was also adjunct professor at the Fontana Corrosion Center. With this brief introduction, now Sridhar, you have about 30 minutes. If you can give us 5 minutes for discussion, it'll be wonderful.
Okay.
Yeah, thank you.
All right, thank you for that introduction. Also, thank you, Professor Raja, for inviting me, as well as Professor Shamsundar to make the arrangements. I'm going to talk a little bit deeper dive in one subject related to pipeline infrastructure, but some of the same points that John brought up hopefully will come through. So the main points of my talk will be that reliability of pipelines is important for the economy and the health of our nations. Pipelines intersect public spaces, so maintaining their safety is extremely critical. And pipelines suffer many types of failures. I'll share some of them with you. And so there is a need to consider them in an integrated fashion. That means involve multiple disciplines. And one of the things I'm going to talk a little bit about is the Bayesian network approach. I hopefully convince you that that's a good way to integrate diverse disciplines and ways of thinking. And the last point is that it's not enough that we have data, and model, but we need to have a way to access our knowledge. So we have to go beyond the current AI and machine learning techniques to really actually use the knowledge of people that we have gained over the last many decades. So you know about the pipeline structure in India. It's pretty extensive. It's a lot of production centers along the coast connecting to the inland. And there's about 29,000 kilometers of pipeline according to this database. US has historically had a massive pipeline infrastructure, has about 850,000 kilometers of gas and liquid transmission lines. These are big diameter, high pressure lines operating, at 30, 40 atmospheres. And they also connect various production centers, such as in the Gulf Coast, to inland regions. Of course, now that we are producing a lot of shale gas, the West Virginia and some of the areas in the Marcellus Shale also contribute to the gas that is being sent along these pipelines. And if you look at all the distribution lines, which are the low pressure lines that are coming into the businesses and homes, they constitute about 3.5 million kilometers of gas pipelines. So that's a large network that intersects a lot of public spaces. So safety of these lines is extremely critical. Now, we may be impressed by these numbers, but one thing we need to think about is our human body has 100,000 kilometers of pipelines, operated by one compressor station, but managed by a supervisory control and data acquisition system, similar to pipelines. That's called our brain. That's got about 100 billion neurons. The number of neurons in each of our brain exceeds the number of stars in the Milky Way. And if you look at all the connections between all the neurons and other neurons, it exceeds the number of known particles in the universe. So we have an impressive computational system and a system that monitors our internal pipelines every day of our lives. Nature has done that over 4 billion years of evolution. And that's really our ultimate goal, is if we can make our pipelines monitor the way our human body monitors our pipelines, we have achieved something. But we are far from that. We can look at the incidents in the US on both liquid and gas lines. Incidents constitute any kind of leak and accidents as well. And you can see that it's concentrated where there is a lot of pipelines, obviously, in the Gulf Coast of Texas and Louisiana. But there are also some additional pipeline corridors where there are increased incidents, and as well as in the California coast. And these incidents are maintained through a pretty extensive database that our US Department of Transportation Pipeline and Hazardous Materials Safety Administration maintains. So that's something that's very useful, because this extensive database provides a way to validate our models as well as get input for our models. Natural gas and liquid pipelines suffer from many causes that are corrosion related as well as non-corrosion related. So here is a sampling of various disasters we have had. External corrosion, this was close to where John lives in Virginia. Basically, this explosion occurred because a rock had contacted a coated pipeline that provides a way of shielding the cathodic protection from protecting the pipeline. So this pipeline corroded in an extensive fashion, causing this burst and failure. This famous example killed 8 people that were camping near the pipelines. This is due to internal corrosion of somebody accidentally leaving a pool of water inside otherwise a dry natural gas pipeline. This is one of the most expensive onshore pipeline failures. That's caused by near neutral pH stress corrosion cracking in Lake Michigan. Cost about $1 billion worth of cleanup, as well as the largest fine that was issued by the regulator to a pipeline company in the onshore pipeline industry. You would think that we would learn from all these failures, but this latest one is in 2021 in Arizona, caused by high pH stress corrosion cracking. Just to give you a flavor, the high pH stress corrosion cracking, the first failure happened in 1965. And we have had massive amounts of research done in this kind of a failure mode. So these failures still happening is a cause for concern. Another one is a corrosion under insulation. This led to a major leak of oil along the California coast, required massive cleanup of the California coast from the heavy oil. This is from construction equipment hitting a pipeline, causing the burst of the pipeline, and the construction equipment ended up, somewhere over here. You can see the burned char of the construction equipment. This is in New York City, where an electrical cable was overlaying a pipeline, causing straight current from the electrical cable to go through the pipeline and cause very high external corrosion and fire in an apartment building. This is one of the most recent one from a supercritical carbon in Mississippi. You can see the frost and the carbon dioxide escapes. It lowers the temperature quite a bit, so you can see a big ice formation around it. And this lowering of the temperature causes the steel to go from a ductile to a brittle transition, and that also increased the fracture. One of the issues here was that the CO2 pooled in low-lying areas and caused asphyxiation of people. Fortunately, no one got killed, but the emergency vehicles that came to take people away could not operate because gasoline-powered cars need oxygen, and this area was full of CO2, and so they had to find other ways of evacuating people. So all these incidents highlight continued vigilance. Now, if you look at significant pipeline incidents in the US, PHMSA, of course, maintains a database. This is from 2003 to 2022. And the startling finding here is that the number of incidents hardly have changed. You go through some ups and downs, but if you think as corrosion engineers, we are doing a fantastic job, it should decay, but it hasn't done that. Of course, from 70 to 79, there were a lot more incidents, and so there has been a decreasing trend, but this is a cause for concern that are we addressing the problem the right way? This is incidents by cause, and you can see external corrosion. This is three different time periods, 2010, 2016, and 2022. And you can see that external corrosion is one of the bigger contributors. Bad specification or operation of equipment is another major contributor to failures. Stress corrosion cracking is down in the weeds, although some of the stress corrosion cracking incidents have led to major failures. So why do failures happen? We can attribute it to four different major causes. One is omission, that is neglecting known principles. And we can solve this by improved regulatory oversight, better quality assurance to make sure people are doing the right things. The other one is transmission, that is better transfer of knowledge. And this is where societies and universities and other training programs play a big role, because we develop standards, we have all these tools to assess corrosion, we have workshops like the one we have now, and worker training is required by regulations, especially pipeline regulation. So we have a good handle on these two issues. The most egregious problem is commission, that is, you know that you have to take some action, but you don't take it for various reasons, usually resource pressures, project deadlines, and so on. And this has to be solved. And one thing universities and training centers play a big role is to really reinforce this idea of professional ethics in carrying out your activities. But we also need better quality control. For example, the issue about bolts that are not meeting standards intentionally require better quality control. And of course, strict enforcement is lagging solution. If you find somebody, they won't do it next time, but it doesn't solve the problem completely. But the last most important step is imagination. That is, how do you use existing knowledge in novel ways? And this is where integrated modeling comes into play. This is where the expertise that we have gained over years of research and knowledge accumulation comes into play. And the reason we miss these failures is because we fail to combine our knowledge and identify ways things could fail in new ways. And this is, in a way, what I'm going to talk a little bit about today. So I'm going to show two examples of internal corrosion in SCC, and I'm going to go through it pretty fast in the interest of time. So internal corrosion occurs because whenever water contacts steel, you have potential for corrosion, but water alone doesn't cause corrosion. You need impurities in the natural gas in the form of CO2 and H2S and oxygen that influence the corrosion. And you also have microbiological colonies. And of course, you can inhibit corrosion by adding organic inhibitors. And of course, sometimes you get sand from production, so you get these solid particles that cause erosion. And then if you add solvents like ethanol or supercritical CO2, they can affect localized corrosion as well because they solubilize other species. So there is a bunch of factors that affect internal corrosion. In addition to that, there is a flow that occurs in the pipelines, and these cause various flow regimes. The most of interest for corrosion is annular flow, because you have water, which is the gray film that constantly contacts a pipeline, and the gas flows through in the annular space. And so this would be a greater concern for corrosion. But you also have slug flow, where you have slugs of gas that flows through, so you have intermittent contact. And these flow regimes differ whether the pipelines are vertical or horizontal or somewhere in between. And one way to think about it is probabilistically. So here, the probability is just plotted as color codes of various flow regimes are plotted in terms of superficial velocity of gas, that is equivalent velocity as if the gas is completely occupying the pipeline, compared to the superficial velocity of liquid, which is the equivalent velocity of liquid if it occupies the total cross-section of the pipeline. Of course, in a gas-liquid mixture, there is a proportion of these two, so they occupy a partial cross-section of the pipeline. And you can see that annular flow becomes predominant when the pipeline is facing vertically down. When the pipeline is facing vertically up, there are some regions where annular flow becomes important. So flow model has many uncertainties, and we have to capture these uncertainties. Corrosion models also have uncertainties, and we have to find a way to capture them. There are many mechanistic models, and in fact, if you look at the NACE standard or AMP standard, the Appendix B lists a whole slew of models. Most of them are proprietary. So the question is, how do you tap into these? Fortunately, I happen to have access to this model, OLI system. And what I do is I exercise this model against a whole host of variables and develop a parametric expression. And that parametric expression then can be used in a Monte Carlo simulation to develop a probability distribution function. And other people have done using other models. For example, Ohio University has a model that can be used as well. So the limitations of all these things is it doesn't capture all the uncertainties. It doesn't capture all the other things that are going on in a pipeline. So how do you integrate all these things? So to do that, a Bayesian network is a good way to do, and I'm giving you a very simple example here. So if you have a CO2 partial pressure, but you don't know what the value is, so you assign coin toss, 50%, it's 0.1 to 0.5 atmospheres, and 50% is 0.5 to 1 atmosphere. And you don't know the temperature, and again, you assign a probability, and it gives you a probability distribution. And here I've used a well-known DeWarden-Williams equation that equates corrosion rate to partial pressure of CO2 and temperature. Now, the advantage of a Bayesian network is, what if you know the corrosion rate through inspection? So now you know that the corrosion rate, it says, well, most likely your partial pressure of CO2 is high, and there is also a good likelihood that the partial pressure of temperature, the temperature is high as well. So basically, Bayesian network allows you to update your input factors based on your knowledge, which is based on the data, which is inspection data. But what is entombed here is the research knowledge that was gained out of laboratory experiments, not out of just data correlations. So here we can do the same thing using multiple other variables, oxygen and H2S, and we use the Ohio University model, run it millions of times to get a big probability distribution table, and that's incorporated in this probability calculation. So basic idea is that the Bayesian network provides you a graphical representation of the causal knowledge that we have developed over the years through much research done in this field. But of course, the pipeline is much more complicated. What I showed you is just one box. You have the flow box, which tells you when the water wetting is going to happen. You have the erosion box, you have the microbiological corrosion, and so on and so forth. And eventually, you're interested in ultimate failure of the pipe, so there is a fracture mechanics component involved in it too. So we can go through these models, and what we have to ultimately do is how valid is this model, and we can test it. So here is a pipeline in China that we tested the model, and the pink bars are the predicted probability distribution, and the line is the actual inspection data, and a reasonable agreement between that. So the idea with these kinds of models is, as you integrate these diverse tools, you have to constantly validate against existing field data. Stress corrosion cracking is a much more complex problem, mainly because you have now a load involved and you have coatings involved. So in a stress corrosion cracking, invariably happens under a despondent coating. So coating adheres throughout the pipeline, but at certain locations, the coating tends to come off, called the desponding process. And in this location, the water from a hole in the coating accumulates and you get reactions. That's because the cathodic protection doesn't permeate all the way through into this region. And what is known is that the crack growth rate is a critical function of the potential, so it occurs only in a narrow potential region. So in this area, the potential is much more negative than minus 750. There should be no cracking, whereas in this area, the potential in this regime, there is cracking. And of course, the cracking growth rate depends on the frequency of loading, which depends on the pressure cycles, how fast the compression occurs in the gas stream. And it also depends on the temperature, because from the compressor, there is an adiabatic heating of the gas, and the temperature rises near the compressor station, and the crack growth rate can increase. So what is really important in this slide is that to model the stress corrosion cracking of the pipeline, you need to know the potential and loading history, as well as all the external soil conditions, the type of coating that is present, and the water table movement that happens seasonally. So this requires putting together an enormous range of disciplines to get at this problem. And that's what we've kind of done. So we have looked at the coating SCC model in chunks. There is a coating despondent module. There is a module that predicts the surface potential using reactive transport modeling. There is a model that predicts the chemistry, and there is all these crack growth rate models. And the reason SCC has a low probability is because all these things have to come, it's a Goldilocks syndrome as they call it, all these things have to come just the wrong way for a pipeline to suffer from SCC. That's why it has a low probability, but a high consequence. So we go through this model, we can model this. For example, coating despondent occurs because soil shears the coating, and that occurs because you have rainfall and you have a low slope that moves the soil. But if you have a lot of vegetation, that prevents the soil from slipping. So you got to capture all these things that the soil biologists and geologists study. And similarly, you have this potential distribution. So we have done a tremendous amount of modeling to calculate what happens inside the coating despondent, and that's a function of soil chemistry. So we have to capture this as well. And finally, we have to capture the chemistry inside the despondent, and then we have to predict the type of pH that depends on the type of SCC that depends on the pH. There's two forms of SCC, high pH SCC and near neutral, and then that depends on the potential and so on. So finally, this also can be validated. So here is just a brief slide of the validation. What we did was compare it to the number of SCC colonies found in the field versus predicted probability. And you can see there are 32 points in the field that showed no SCC, and the model predicted that there will be no SCC. The model did predict there will be SCC when there was no SCC, which is okay. It's a bit of a over-conservative approach. But wherever there was SCC in the field, the model was able to predict the right type of SCC. So that gives us a comfortable feeling that we have captured all these diverse sources of knowledge and disciplines in modeling this complex problem. And then we can also predict the crack growth rate to match the observed crack growth rate. So to really summarize this complex topic, what I really want to communicate to you is that pipeline is sort of an example of corrosion that involves many complicating factors that come together. And we have done a lot of research. There was a question about how AI and machine learning approaches can be used. But my philosophy is that a lot of the AI and machine learning approaches are, to me, intellectually lazy. We have tremendous amount of research and knowledge that we have acquired, and we need to assemble that in a careful way and develop a better way of predicting these events. I believe that Bayesian network is a good approach because it provides a lot of causal connections. But one of the problems with Bayesian network is communicating that to an organization that has multiple layers, from top-level managers to a very detailed level technical person. So one of the ways that DNV, for example, has been doing, I'm not a advertisement for Microsoft, but we use Surface mainly because a lot of our models are already PC-based, so it was easy to assemble. But the idea was we could put the Bayesian network along a map of a pipeline, so we can point anywhere along the pipeline. It brings up the Bayesian network. But this is the highest level of the Bayesian network. So the high-level manager is only interested in whether a pipe is going to leak or not. But if you can go into any of these nodes, you can press the button, you can drill down, it brings the next layer of Bayesian network that's a bit more detailed, all the way down to the bottommost level where a corrosion engineer is highly interested in, looking at how that was arrived at. So the idea with this is that we need to have a better way of communicating what we are doing to decision makers within an organization. And this is an ongoing field, so the Bayesian network provides a framework to assemble what we have gained in our knowledge. So with that, I'm stopped. I hope I didn't go over too much time, Raja, but I'm open for any discussion, and you're always welcome to email me if you have questions.
Yeah. Thank you, Sridhar. A couple of questions we can have. If you can come on the video, it's okay. Yeah, it's open for discussion. Yes. You have some questions? Can you please identify yourself?
Hello?
Yeah.
I'm Abhinav Oja from Nuclear Power Corporation India Limited. So we have program of in-service inspection which be based upon the probability of failure of a pipeline. That is based upon some numbers we generate, based upon some probability of failure based upon some models, say stress corrosion cracking or fatigue crack growth. So whether there are any commercially available softwares are available where we can predict the probability of failures, and based upon that we can increase the periodicity of this in-service inspection, because this increases our refueling outages during which we do in-service inspection. So whether Sridhar sir or MC consultant has done any work in this area?
Yeah. Okay. Yeah.
Partially heard it.
Okay.
So if you can rephrase it, that'd be great.
So, okay, see, there are certain pipelines. It is from Nuclear Power Corporation of India Limited, and you have underground pipelines.
Only limited underground
No,
pipelines.
what you are talking about is underground pipeline, or
No.
is it internal corrosion or external corrosion?
Mostly internal. In certain cases, it may be both internal and external, like.
And what kind of pipeline are they actually? Are they
some
water?
Of them are low alloy steel. Some
No,
of
I
them
mean, what do they carry?
they sometimes carry steam, sometimes water.
Okay.
Yes.
So yeah, so the idea is you have been talking about mostly the pipelines buried in the soil, and also meant for carrying the oil and gas products, right? So are there any models which are available in a broader sense of the pipelines that carry the steam, for example, or maybe water? I guess I think the one on the soil side is same, right? Irrespective of whether it is whatever it carries, right? I think so. The Bayesian model must be applicable in that case.
Yes, I think there are models for water pipeline, cooling water pipelines in nuclear power plants, for example. There are flow-induced corrosion problems. And people have developed models. And the idea here is if you have the model, or if you have the data that can be regressed into a model, then you can use that in a and develop probability distributions, because all these models have a lot of uncertainties, both in terms of how you regress them, the parameters, as well as the input data, flow rates, pipeline inclination, and so on. So in principle, all those things can be accommodated. The real work is getting at the knowledge base that exists in that field. For example, flow-induced corrosion models exist in the nuclear power plants, and capturing that in the probability models.
But are these models available commercially? Are there software packages which this? I mean,
some of them are proprietary, as far as I know. This is not something that I have delved into deeply, but there are published models available for cooling water corrosion issues.
I hope it's okay if I give your communication for further discussion with the people.
Sure, it's not a model I can trot out readily, but I can certainly point you to the right direction in terms of getting at those models.
Yeah. Thank you. Dr. Jaya Rawat from PPCI.
I have a question for any experience on ethanol blended gasoline cross-country pipeline transportation regarding some software or some street and on this.
Yeah. The question here is, are there any experience in dealing with pipelines carrying ethanol blended gasoline?
Yes, there is a lot of experience. The pipelines, there has been only one known, maybe two, but one I know of stress corrosion cracking. So the main problem with the ethanol is it causes stress corrosion cracking of steel. As long as the gasoline volume ratio is below roughly about 30%. And anything above 30% gasoline in ethanol, the stress corrosion cracking goes through a maximum around, I would say 50%, and then decreases after that. So what do you do for pure ethanol that has only 10% gasoline? There are two ways. One is to reduce the oxygen content, and that's really difficult to do in a pipeline. The second way is to add inhibitors. So there has been quite a bit of work done on adding inhibitors to prevent stress corrosion cracking of pipelines. So there is a lot of published data available on stress corrosion cracking of pipeline steel and ethanol. I know Ajay Krishnan was involved in some of that, so he may remember if he's there in the workshop. But certainly I can send a lot of information on that, if that's of interest.
Okay, yeah.
But there has been quite a bit of experience. And it seems to vary from one country to another. At least the claim is that the Brazilian ethanol is a bit more benign than the corn-based ethanol in the US, but so far that has not been completely verified.
Okay, I would connect the person with you later. Okay.
Did I have one?
Only one last question, if you don't mind. It's okay for you if I provide your contact number with the participants?
Yeah, the email, yes.
I mean that. That's right. Okay.
Yeah.
Thank you, Professor Sridhar, for a very nice presentation on stress corrosion cracking. I just have one question. Could you say something on repurposing of existing pipelines for the hydrogen gas transportation? How good, how bad, especially with regards to hydrogen embrittlement and stress corrosion cracking?
Well, this is a subject of ongoing work. I mean, I'm involved in a major project in California because state of California wants to repurpose, wants to make our economy more hydrogen-based, and that involves repurposing our gas pipelines with hydrogen. The main concern, of course, is the hydrogen embrittlement of steel. And the concern is the reduction in fracture toughness, as well as the increase in crack growth rate with hydrogen. One concern is that even small amount of hydrogen seems to significantly reduce the fracture toughness of pipeline grade steel. But what is unknown is the actual pipeline operating conditions. In other words, the pressure cycles, the operating history of the pipeline, and the natural gas quality. In other words, the impurities in the natural gas, oxygen and moisture and CO and CO2 and so on, and their effect on hydrogen embrittlement. So that's some area of ongoing research that we are doing. At present, most people feel comfortable with about 20% hydrogen in natural gas blend. Of course, for the low pressure pipeline, once you get to the distribution system, perhaps there is less concern of hydrogen embrittlement. But there is more concern about polymeric materials, and that's another ongoing area of research, both for structural polymers used for tubing, low pressure tubing, as well as gaskets and seals, because hydrogen tends to swell the elastomeric materials. So the question is, what happens if you have a high pressure hydrogen and then you decompress the hydrogen, what will happen to those seals? So, and then there is a whole host of issues on the burner end. If you burn hydrogen, you emit more NOx compared to natural gas. And so would you exceed the environmental quality for NOx? So we are addressing this whole issue of hydrogen infrastructure and how much hydrogen you can put in, all the way from the pipeline delivering the blend to distribution system to the end user.
Thank you.
Yeah, so thank you very much. I know there are a lot of interesting questions, and we are running short of time. So Sridhar, let me thank you on behalf of myself and the organizers and the participants for the wonderful presentation.
Thank you very much.
I think now we have physical mode of presentation. So